from whichever reference frame you choose to be in, whether you're stationary or in uniform motion. So it's pretty interesting. A consequence of this is something called the addition of velocity, where from Leona's perspective, when she walks onto the moving walkway, she has a certain velocity to herself, but then all of a sudden the rest of the room around her starts moving in the opposite direction with another velocity. But from an outside observer, from our cameraman, it's not the case that the entire building is moving, but it's simply that her velocity was added to the moving walkway. And I'll play that for you. So Leona has a beginning velocity while walking pretty steady, slow, and then as she steps onto the moving walkway, her velocity is increased by the velocity of the moving walkway. Except from her perspective, she's still going the same speed. Here's a side view. She sped up once she stepped onto the walkway, and that's just a simple addition of velocity. This is going to become important later on, even though it seems like a simple idea. Here's a cartoon. So here's a guy on a Segway. He's going velocity v. But as you pull out, from our perspective on the beach, he's actually moving on an aircraft carrier. The aircraft carrier's velocity is w. So, from our perspective, the man on the Segway is not simply going the velocity v, but he's going v plus w. His velocity on the Segway plus the velocity on of the aircraft carrier. This is a consequence of maintaining the relativity of motion. So that's a brief history for you of this idea of relativity. That there's been an idea of the relativity of motion for a while, before Einstein. What Einstein added to this was, it seems lawful that all the laws of mechanics are going to be able to be viewed equally, whether you're stationary or in uniform motion. That they're not going to change just because you're in motion. But what about the rest of the laws of nature? Are they going to be maintained? Are they going to be able to be viewed equally, whether you're stationary or in motion? For example, Leona wanted to test this out. So are people familiar with a solenoid? Do you know what it is? You have a magnet going in and out of a tube which is wrapped in wire. And the motion of the magnet induces an electric current. This is her playing with it stationary, standing still. When she steps onto the moving walkway, is the solenoid still going to work, or are the laws of electromagnetism going to change? A lawful follow-up to our idea of the relativity of mechanics. Will all of nature's laws be maintained whether we are stationary or in uniform motion? So Einstein pondered this for a while as he was a kid. And one of the questions he pondered over was, what about light? If I chase after a ray of light, is its velocity in relation to me chasing after it going to decrease? And if I chase after it long enough, if I manage to catch up with it, will it no longer be moving? As if two cars on a highway, relative to a police officer standing on the side of the highway, they have two different speeds. Say one's 30 miles an hour, another 60 miles an hour. But to the perspective of the person in the car going 30 miles an hour, the car in front of him going 60 is merely going 30 miles an hour more than him. In his reference frame, the second vehicle is going 30 miles an hour, even though to the police officer standing off onto the side, it's actually going 60. So is that going to also happen to a ray of light, being a consequence of the addition or the subtraction of velocities? If you chase after a ray of light, will its velocity decrease as yours increases? And will you eventually catch up with it? If you're the two cars on the highway and you eventually end up at the same speed as each other, both going 60, if you turn and look to the other passengers in the car, they seem stationary. It seems as if both the cars are parked, just looking at each other. So to Einstein, this was a puzzling idea. What would light do if you chased after it, and if you caught up with it? Would it all of a sudden stand still? So here we have two police officers. One on the left, both of them have clocks and speed guns, speedometers. The one on the left is going to clock the speed of the police officer on the right. The one on the right is going to clock the speed of a culprit. A ray of light. So, as the police officer increases his speed, as perceived from the stationary police officer, the more chubby guy, the speed of the ray of light is decreasing. And now we have space travel. And now he's at an equal speed with the ray of light. So we laugh. It's a funny thought to be chasing after a ray of light, for it to decrease its speed as you catch up with it, and then for it to appear stationary, whatever a ray of light would look like stationary. While to the police officer who stayed behind, for good reason, would see the ray of light at its constant velocity of 186,000 miles per second. So this was a difficult situation for Einstein. It seems in the law of mechanics that there is no absolute rest, that all motion is relative. But to the laws of optics or electromagnetism, there seems to be an absolute rest, unless that being the velocity of light, the constant velocity of light, maintaining that there's some absolute rest somewhere in which it's being measured by. And if we were to change the velocity of light and say, no, the situation for light is going to be similar for the situation of mechanics, that all motion is relative, and that your velocities are going to change in relation to each other, then the velocity of light is no longer constant, but your laws of optics, your laws of electromagnetism, which act at the speed of light, are now changing. They're no longer laws. So this was very puzzling for Einstein. He didn't know what could give. He didn't want to doubt the constancy of the speed of light, because then you would lose all the laws and all the facts that we've learned from experiments of electromagnetism and of optics. But he didn't want to assume that there was, or to not to assume, but to compromise and come to the conclusion that there was some absolute rest, some point in the universe that acted as an origin to the speed of light. He didn't want to have to come to that conclusion. So, in order to resolve this difficulty, he said, let's just set up a simple experiment. If the velocity of light changes in relation to your motion, then with an experiment you'll be able to detect whether or not you're moving. Where with the Newton's cradle or any other mechanical experiment, we're not able to determine whether or not we're in uniform motion, because the laws of mechanics are going to act the same whether you're stationary or whether you're in uniform motion. So there's no law, or there's no experiment in mechanics to indicate to you whether you're in motion or stationary. But if the speed of light is going to change in relation to your motion, then you can set up an experiment using that to determine whether or not you're stationary or in motion. So if we can come up with a precise experiment, we'll be able to determine if the velocity of light is relative, then it'll change when it's in a system that's in motion, or whether or not it's constant and the laws of electromagnetism are maintained. Einstein found out later that there was an experiment like this set up, the Michelson-Morley Experiment. We got a chance to replicate the experiment. So you have a light source, 3 mirrors, one in the middle which is half silvered, so it allows half of the ray of light to continue in its forward direction, and the other half to be reflected by this 45-degree angled mirror perpendicularly to the other ray of light. The other 2 mirrors are placed equidistant from the center mirror, so that the 2 rays of light will be split in the middle, reflect off of their 2 targets, and be collected back into this interferometer here in the left corner. The interferometer is used to measure the interference waves of the 2 rays of light, whether they're in sync or whether they are off rhythm from each other. So the experiment wouldn't seem to do much